So the whole reason that we need to talk about the atom is because of these positives and negatives, right? These protons and these electrons. So where do you see these electrons? Because this is what's going to be important for today. Where are they located in the atom? Ads?
In the middle.
The electrons?
Yeah.
Oh,
they orbit the nucleus.
Very good. So they're on the outside. So if I had all of you guys get into like a big group, like a big huddle, and I take a fire hose and I start spraying you, who's going to get hit with the water first? People on the inside of that huddle or the people on the outside? What do you think, Paul?
Outside.
Absolutely. So if you think of these electrons, they're on the outside of the atom. So if you have other atoms that are around and they're moving around, doesn't it make sense that it's the electrons that would have the opportunity to possibly be taken away from an atom or maybe be taken added to? Yeah, right? So it's going to be the electrons that are going to change. It's not going to be the protons. And we're going to talk a lot next year how the proton number stays permanent for the atom. And they talked about that in the video. So it's the electrons, that number is what's going to change. And when you get that uneven number, go back a second. When you get that uneven number of protons and electrons, what do we call that? So if they're even numbers like 5 and 5, 5 protons, 5 electrons, we call that neutral. What is it called when they have an uneven number? The atom would be what?
Charged.
Very good. It's charged. And again, it's a simple idea, and I'm not sure why so many people struggle with one, like they just don't remember that. And so it's just charged. Okay? So again, it's not like charging up your cell phone, charging your battery. It's like unequal number of protons and electrons. Here it's even. This atom would be considered neutral. If we would add some electrons, then it's not neutral anymore. It's now charged. If I would take one or two of these away, it is now charged. So it all depends on how many total electrons and protons you have, right? If it's uneven, then you're charged. And so if you have one thing that has more positives now, or one thing that has more negatives now, those items are going to come together and attract. If you have two items that are positive because they have more protons now, they're going to repel. And show me with your hands what repel means. Good. Show me with your hands what attract means. Perfect. And then if you have two items that are negative because they have more electrons, they're also going to repel. So this is going to be important with electrical fields and magnetic fields both. So attracting if they're opposite charges, repelling if they're like charges. And that's going to be something that you're going to definitely need to know 100%. So one of the best ways to create a charge on something is for things to like rub back and forth or like rub past each other, whether it's tumbling, whether it's rubbing, whether it's just sliding, that causes those electrons that are on the outside of the atom to maybe be pulled off, right? And if you have less electrons, now you have more protons, which would make something positive. If another item is taking on those electrons, then now they have more negatives and they become negatively charged. And then we get these invisible kind of movements happening, the attraction or the repelling. Okay, so this happens with clothes in a dryer. Who here has ever like lost a sock and it's been like stuck to a sweatshirt or something and you're like, and you separate it and the sock was stuck to the sweatshirt, right? Or the t-shirt. Happens a lot. If you don't put a dryer sheet in, the dryer sheet helps to keep things neutral so that they don't build up charge. But the whole point of a dryer is for things to be rumbling and tumbling around. It's a perfect situation for electrons to be kind of pulled off of an item. Okay. The other thing is that we're kind of getting to that time of year when the heat's starting to kick on a little bit. Not so much this year, but here soon. And so what happens when you take your sweatshirt off and you pull it over your head? This might happen more to people with longer hair. What happens to your hair a lot of times?
It frizzes up.
Frizzes up. Ronan's patting his hair. He's like, that's happened just a few times, right? You get a little fluff going, some static, right? So it's the same kind of idea. Electrons are being pulled off of those items, right? So that means that if we're talking about the clothes in the dryer, clothes are gaining or losing electrons. Some of one piece of clothes is pulling electrons off, one piece of clothes is losing electrons. So now you have one that has more electrons and negative, one that has less electrons and is now positive, and that's why you get them sticking together. Okay? So we said the whole idea with this invisible force field that's at work is that it has to have the appropriate property of charge. Okay? So appropriate property is kind of weird, but if everything is neutral, then you're not getting any attraction or repulsion. So you're not getting any of that motion. You're not getting any of that like invisible force at work to pull things together or to push things apart, right? So I have kind of a gross example, but we've probably all been there. So have you ever been walking down the hall and all of a sudden like you walk into like a fart? Like you're walking and you're like, oh no, oh my, like that, woo, ugh. Does that happen to anybody? Or maybe like walking into, you liars, you guys lie. You've never been like walking like and all of a sudden like you don't hear a fart, but like you walk into it, you smell it. Henry wasn't lying. He's like, yeah, it's happened. Right? I'm not saying you caused it. I'm just saying like somebody farted and you walked through it. Yeah, they're like, oh my gosh, are we really talking about this? I call this the fart funk situation. Okay? So like you're walking or anywhere like, and all of a sudden it's just like, oh my. And like you keep walking and you're like, whoo, I'm out of it. Right? So as you approach the origin of the fart, it becomes more intense, right? You're walking, not bad, and then it's like, ooh, I smell, oh, and then you're like, try to hurry up. And as you move away, and can you see the fart? It's not a cartoon, it's not like a green bubble gas that you walk through and like you see, right? You know, like on a cartoon, they always have like that little yellow or green, kind of like your sweatshirt color, sorry. But kind of like that color, like we don't see a fart, we just, maybe you hear it if you're close enough, but we're saying you don't even hear it. You're just like walking through and you're like, oh no, right? So you try to hurry up and get out because you don't want it to stick to you. That's like an appropriate property. If you are walking, or it's like a force field, you don't see it. The closer you get to it, the more intense it becomes. It's exactly like a force field, all right? The other thing, what if you are really sick? Like, I don't know, it never happened to me, I never had COVID, but a lot of people said that you lose your sense of smell when you get COVID, or it's a possibility. So what if like everybody around you is like, oh my gosh, this is terrible, and you're walking, you're like, I don't smell anything. Like you lost your sense of smell temporarily because, you know, being sick, or maybe you're stuffy, or maybe you had COVID, whatever it may be, you don't have the appropriate property of smell at that moment. So it's not gonna affect you. You might just be like, okay, that's kind of weird. Like I don't smell anything, and everybody else around you is like freaking out. That you wouldn't have the appropriate property. But if your nose is functioning properly, and you're walking, and there's a fart, and you walk into it, you're gonna smell it, right? So that's what we mean by appropriate property. If you have if there's an electric field, it has to be because the items are charged. If everything would always stay neutral, you're not going to experience that attraction or repulsion because there's no charge. So charge is the appropriate property, okay? And the other two force fields that we'll look at have their own appropriate properties, but for electrical, it is charge, okay? So you have to know that what charge is, you have to know that that's the appropriate property, and you have to definitely know these things. Attraction for opposite charges, repulsion if they're the same charge. And if it's neutral, they're not going to do anything at all. Like if everything's balanced, you know, there's not going to be any attraction or repulsion. Okay, so that's our staticky situation. And so one example of this is static electricity. You have a gathering of excess charge on an object. And so this is slide 8. And it says how to build up an electric charge. Kind of mentioned this with the dryer. But materials are made of atoms, and normally they are electrically neutral. They have an equal number of protons and electrons. So you have equal number of positives and negatives. And so you have to make that unequal somehow. And again, it's going to be those electrons that are on the outside of the atoms that make up that material that will cause the item to become charged. So you're either taking electrons away or another item is gaining those electrons. So some are stripped off and then they accumulate on another item. And so this can happen by rubbing two objects together. And usually, we talked about this, like pulling a sweatshirt off, kind of like those dry fit sweatshirts more than the cotton ones. Those typically will cause kind of like pull the electrons off of you, off of your hair, and you get that static happening. But the electrons move from one material to the other, which leaves an excess of positive charge on one material and an equally negative charge on the other. And you're not going to have to like predict like which one's going to gain the negatives and which one's going to lose the negatives or the electrons. But just as long as you understand that, the more unbalanced the number is, the greater the charge is. And we'll look at a little simulation that shows this. Did I go? Good. Okay. So take a look at this. Let's pretend that there's only one balloon here. Okay? So we're not looking at, just look at one of the balloons, not the three. So one balloon there, one balloon here. Which picture do you think is showing the greatest static electricity? Which one do you think, Logan? Okay, so this one? Anybody like this one? I have a few yeses, kind of split. Okay, so remember my example with the fart funk. Let's pretend like my phone is the origin of the fart, right? As I'm walking, what's happening as I get closer to the phone, or that origin? It gets stronger, right? Okay, so that's why the one on the right is actually the right answer. This is actually stronger. She's having to hold it. You can see the static, but here it's actually held in place. Like he's not even having to hold it. Maybe if she lets go, the balloon just falls. Maybe it's not going to like draw right to her head. But his is so strong that it's holding the balloons in place. And again, it's not because there's three of them. It'd be the same if there was just one. Okay, so the closer you get to the objects, like the closer the objects are, the more intense the field is. Okay, just like the video that we watched where the people were walking, the characters were walking through the forest, right? Or the jungle, kind of. And the closer he got to that force field, like Katniss, she could kind of hear or like she could sense something was weird. And right before Peeta hit into it, like she knew like he was at it. And so like the closer you get, the more intense it becomes. Same thing with the smell, right? The closer you get to that origin, the more intense. I have another story. It was years ago. My son played travel ball and we were getting ready to leave for a week. And so like we were packing, like everything was kind of chaotic. And like I walk around the front of the house and I'm like, oh no. I'm like, oh shoot, I smell a skunk. I'm like, oh my gosh. And I look and our little Jack Russells had a skunk trapped under our porch. And like I could see because we have like that lattice stuff. So like I could see in there and I was like, oh my gosh. And so like, obviously like I stayed far away from it, but like as I was walking and I couldn't find where it was coming from, I kept getting closer and closer. I'm like, where is it? Like, what is it? Where is it coming from? And there it was, right under my front porch. And so like, obviously like the closer you get to the source, which was the actual physical skunk, because they had killed it and drug it under the porch, which is very nice of them, it was more intense. And so obviously, and like I remember it because I was like, oh my gosh, like everything, like it was starting to come into the house, and like we were packing. I'm like, we're gonna take this skunk smell with us to Tennessee. Like this is not gonna be good. So I remember, and it was a long time ago. I was like, whoa. But the closer you get to the source, the more intense it becomes. If you think of smell, same thing with these force fields. It's a characteristic of all three of them. Excuse me. The closer you are, and in each one we'll kind of say, but here the closer that the objects are together, the object with the positive charge and the object with the negative charge, the closer they are, the more intense. So, and if you relate it to that fart funk, it usually is pretty clear. So, this also, static electricity also happens to help create lightning. Okay, so within the thundercloud, you have these tiny bits of ice, which is frozen raindrops, bouncing and bumping into each other. So I'm not sure if you need this word, but it's frozen. Frozen raindrops bump into each other. So kind of like clothes in a dryer, right? They're rumbling and tumbling and rubbing all over each other. And so these little tiny collisions create an electrical charge. So some of the electrons are getting pulled off of some of the raindrops, the frozen ice, and some are becoming the ones that got the electrons removed. And so you have the positively charged protons kind of forming at the top of the cloud, and the negatively charged electrons or atoms are at the bottom of the cloud. Well, we know that opposites attract, right? So at some point, they want to become neutral, like they're trying, like their natural state is neutral. And so since those are attracting, that positive charge at the bottom is going to be attracted right there. So it's causing, if we have positive in the cloud, then we have negative, and then we have positive on the ground, at some point it's going to want to what we call discharge and cause it to go back to neutral. And so the charge at the bottom of the cloud, which was negative, eventually wants to connect with the positive charge that was on the ground, and it creates that lightning strike. I'm going to go back for just a second. So if you watch up here, watch the picture. So the charge builds up in the cloud, you get the negative, and then you have the positive that builds on the ground below it, and then the lightning strike causes it to discharge and go back to neutral. So you can see it again happening. So lightning, static electricity on our clothes, or between anything. If you've ever gone down a slide, this tunnel one especially, because it's all around, but your hair will get, like, you can feel like that static buzz, that fuzz, like your hairs might stick up even on your arms. So what's happening is, obviously, your hair starts to stand up. Well, the reason why is because as you have that friction of sliding down the slide, it's pulling electrons off of you, right? And so we know that opposites are going to attract. So if you're losing electrons to the slide, you're now positively charged, the slide is negatively charged, it's going to be kind of like trying to attract. And then what do we also know about, like, if you have two positives, what are they going to do? See a few of you going like pull apart, right? They're going to repel. So if your hair is positively charged, all of those positive hairs want to get away from each other. So that's why it's like, doesn't just go like in a perfect clump, like you're not having a clump go, like it's all wanting to like spread out and get away. So the positives are wanting to get away from each other on your hair, and they're also being attracted to the negative that was created as those electrons were pulled from you, which caused you to get positively charged in the first place. okay? And so those positive hairs all want to push away and repel each other. It's kind of two things really happening there. But it all is because you create an unequal number of protons and electrons. You get that charge. Okay? And that's how each hair ends up standing straight up and pushing away from each other in all directions. Pretty simple? Not terrible-ish? I think, yeah, we're gonna stop there. We have some videos that we need to take a look at.